Let's get going for today. Just to kind of locate ourselves, where are we in the class? We have had 5 lectures, and I missed the one on Tuesday, but I'll make up for this missed lecture sometime very soon. So just to be, we are around topic 3 right now, and today and the next class we are going to focus on 3 and 4, and really these two topics are at the heart of semiconductor nanostructures and physics of semiconductors. So we were developing the physics necessary to explain a lot of things that we will now talk about, right? And the plan is before your let's see, next Tuesday is a holiday. It's a break, right? Next Tuesday, and Thursday we do have a class, and I want to check if we use the office hours of the Thursday as a review session of all the things we have done till now. Can everybody make it Thursday? What was it? 5 to 6:30. Right? 5 to 6:30. Can everybody make it during that time? Right? Okay, so that's good. So we'll do that next week Thursday, not today. And my goal is really to get to the end of topic 4 before your first midterm, and I think we'll do that. We'll be able to do that with this topic and the second assignment. So basically, the first 2 assignment and topic 4, 1 through 4 would be kind of the first prelim contents of the first prelim. So. Okay, so and the other thing is again, just it's kind of a reminder that please read through the set of slides, which is extremely comprehensive, and a new set of handouts will be posted either tomorrow evening or Saturday morning, and a second assignment will also be posted before Saturday, basically by Friday, so before Saturday. So okay, that's just a bit of housekeeping. Yeah. All right, so I will need the computer later, but not right now. So let me use this. Okay, so getting back to where we were, so I just wanted to summarize a few things we learned about the free electron in a solid, and we were looking at specifically a one-dimensional problem where an electron was allowed to move in a 1D ring, and from there we were able to write down things like the momentum was h bar times the k of the electron, so momentum and energy was h square and k square over twice mass of the electron, and just because of the fact that the electron is on a ring, not all k's were allowed, but there were discrete values that were allowed, right? 2 pi over L, where L is the circumference times n. Right? So these were the discrete values allowed. As a result, the momentum, only discrete values allowed. Energy, discrete values. Angular momentum, etc., etc. And then we, in the last class, we defined a rather important quantity, which I tried to stress, is the density of states in one dimension. There, the question was, and I want to kind of collect a set of pictures of the density of states. So let's see, in one dimension, I'm going to kind of draw the E and E versus K. And the E versus K in one dimension is really just the parabola, right? This h squared k squared by 2m. And based on counting the number of electron states between any window of energies here, let's say, right? And we can go back here and count how many k states are here. We found a density of states, and we found that in one dimension it went as the energy increased, it went as 1 over square root of the energy of the electron, right? So that's something we found in the last class. And so there's stuff sitting in the front, and then 1 over square root of energy. So just to be clear, only if the energy kinetic energy term looks like this: momentum squared by twice mass, which is the sort of similar to a classical picture. Only then you get this 1 over square root of energy, and only if you're in one dimension. So that these are the things. If I change this to 2 dimension, it will change. If I change the energy dispersion, and this is something you saw in your assignment, if you go to graphene, it won't be quite the same. So it depends on 2 things: dimensionality and this energy dispersion. They determine the density of states, right? So, and today we're going to really talk a lot about density of states, because that question is what answers the difference between metals, insulators, semiconductors, superconductors, and we kind of lead to that. So we focus a lot on the density of states. And the other thing is, this is directly measurable by STM and things like that. You can measure this directly. Right? And based on the density of states, we also said I can define like a total energy, which is the sum of energy and times the occupation function times the density of states, right? This is the total energy. And based on this, we were able to also find out that the average energy per electron in a one-dimensional situation is, you kind of integrate out over all energies here. You can go from 0 to infinity if you might. But then you see that a lot of the energies are bunched together at the bottom. And this is, so you get like, I think, 1/3 of the number of electrons times a Fermi energy. That's the average energy here. Meaning, if I fill it up till here, and this is at 0 Kelvin, let's say that's my Fermi energy, then the weighted average, as you can see, would be a little lower here. So you get 1/3, not half, but 1/3 number of electrons times the Fermi energy of the electron. So that was kind of the average energy of electrons. Now, everything here that we talked about is quantum mechanical, and as a result, you also have at 0 temperature, you have this energy, and that's clearly due to Pauli exclusion principle, and there's no other origin of that. It's purely due to Pauli exclusion principle. To satisfy Pauli exclusion principle, the electrons have to pile up till that energy. The last thing we talked about was the current, and we showed that by applying, writing down the wave function of electrons in one dimension as 1 over square root of length e to the power I kx, and we take that, apply this expression we had for quantum mechanical currents, and from there what we found really was an expression that looked like q times electron charge times 1 over L times the velocity h bar k over mass of electrons, so momentum over mass. So this is what we had found, and it looked similar to q times electron density per unit length, 1 electron times the velocity. So it's very similar to that, the current density. Right? And now we're going to kind of first job today is to take all of these into 2 dimensions and 3 dimensions, the first job, and then show that this quantity can explain the Drude result that we had, that current is conductivity times the electric field, or current density is conductivity times electric field, where conductivity is electron charge squared times the number density of electrons times tau over the mass of electrons. If you remember, this is something that's electrical conductivity, and we can get it also from quantum mechanics, because this is an experimentally measured quantity, and so no matter you apply it through classical methods of Drude or full-blown quantum mechanics, we should be able to explain both of this as well, and we will be able to. Okay? So, but our way of thinking of transport will completely change, and that's something that's the reason I'm going through this right now. I want to emphasize that the way we think about transport in this earlier was this classical particles moving according to Newton's laws of motion, that this will have the full wave particle duality, everything in it. But for this case, you will see that answer is the same. But for many other cases now, you look at quantization of conductance and all that, you cannot explain that from classical picture, but this will have no problem explaining all those things, so which have been experimentally observed. Okay, so this is for 1D, and now we were talking about 2 dimensions, and I want to kind of create a table if you might, and I may even ask you to create your own table in the next assignment, where all of these quantities, you have 1D, and you can write it in 2 dimensions, and then 3 dimensions, and so on, right? So these quantities here, physical quantities. So in 2 dimensions, clearly the wave function we had talked about, it can now move in two. There are 2 free directions to move in, and let's draw a line here. Yeah, so it can move in a plane, and looking at the plane from the top, I mean, we can think of it as, instead of infinite on both sides, we can again introduce periodic boundary conditions from 0, 0, to L, 0, and L, L. L is the length, and 0, L, right? So something like that. We restrict it to a square. You can choose a rectangle, doesn't really matter much, initially at least. Later on it will, where we have if you have a ribbon or a graphene nanoribbon, then this is much smaller. That is much longer. That is much smaller. So, for example, it'll matter, but right now it's not. It's irrelevant. Yeah. So now we release an electron here, and again it is a wave, and it can now move in both directions. And the condition we are imposing is, it's a periodic boundary condition. So if it kind of gets out of this point, it kind of re-enters here again. So it's tied in. It's the same surface. Think of it as a donut surface. So if you wrap it around. But then with all those conditions, all that it does to the wave function now is it makes it 2-dimensional, right? And so the way and this is something in this course you should be able to write down. This is the free electron wave function, or called the plane wave form of a wave function. And here you'll get area, which is L squared, e to the power I, and k dot r, which essentially is kxx plus kyy. And this is something we were in the last class. This is where we kind of ended. And now you can see that the wave function must satisfy x plus L and comma y should be equal to psi of x comma y, right? So that's one periodic boundary condition, and then there's one on y. You can independently kind of satisfy all those things. And to satisfy those things, what you will get is kx comma ky. This is a vector in the k space. So this is the real space picture. Let's plot the k space picture. Kx, ky. 2 pi by the wavelength along x, if you might. And this is now become, because of the periodic boundary conditions, it is a discrete grid, nx, comma, ny. And these are integers, positive, negative, 0, all of them, right? And you have a discrete grid of points here. So, right? And then each of these points now it defines an allowed state for the electron. Just like we had in 1 dimension, each of these points here, now it's in 2 dimensions. Right? Very simple. And then a very important thing is the separation between them still remains 2 pi by L, but now it's in 2 directions, this way and that way. So the area of each of these little squares is 2 pi over L whole squared, right? Each of these tiny squares. And you can see that if I have this sort of fill up this 2-dimensional space, then effectively each state here occupies exactly that area, effectively, right? Because this is shared between 4 neighboring nearest neighbors. So that's the area in K space that each allowed electron state occupies. And this is very important to realize. And it's kind of simple, but sometimes people forget. But this is very important, that if I have an electron state, its wave function, its energy, in K space, this is the volume in general. In 1D, it would be the length. In 2D, this. And 3D, it will be cube of this, right? So that's the volume occupied by a state, a quantum state in D dimensions. So 2 pi by L to the power D, where D is the dimension, right? Okay, so now we can again ask, is that clear? Or any question? And you can see from here that if I, instead of a square, if I had a very thin patch like that, if my x direction was short, y direction was long, then it will, here the x direction will be longer, because 2 pi over Lx here, So it will kind of grow fat and tall or something like that. It will stretch out. And later on, maybe after the break, we'll see that this, whatever happens here is a Fourier transform of there. Any physical property there, do a Fourier transform, you end up here in K space. This is related to as a Fourier transform. And it may not be a surprise because, so yeah, waves, this is a single component of a Fourier series, e to the power I k dot r, so 1k. Each state is 1k state of a Fourier series you might want to expand, so that's the meaning of this. Okay, so now we can ask a similar set of questions. What is the momentum? And clearly here, if maybe you can help me here. Let's say I want to ask, I'm going to choose a state that is, here at this point. So in ky, so it's probably 1, 2, 3, 4, about 6 or 7 times 2 pi by L in the y direction. Right? So which direction is it going in real space? I'm looking at that state. That is one quantum state. It's a eigenstate of the free electron in 2 dimensions. So which direction is it going in? It's going in the y direction, right? It has a momentum of h bar times that k, right? So physically, it is actually going in that direction. Physically, it's moving in that direction, that particular state, right? Similarly, if I have a state here, which direction is that going in? So it's going, in something like that, right? And you can see now that any property I would like to find, if I have a bunch of electrons, not just one, if I have 10 to the power 12 per centimeter square electrons and I want to find the current, what I'll do now is I will find the current due to each k and I'll just add them all up. That's the way to think about anything to do with quantum, any energy, momentum, or net current. We just kind of find the physical property of that state and just sum it overall. And instead of summing, we'll be integrating because these are very closely spaced grid of points. So that's, and this is a thing we'll apply many, many times in the course. So if you are, stop me at this point if you don't feel comfortable with this property. So any physical property associated with the K state, we're going to find it. And then the physical property of an ensemble will just be the sum overall. But as long as we are clear on what is the physical property of one state, we can answer it for the ensemble. Okay, so that's K. So momentum clearly now becomes, it's basically, you can see, it'll be h bar times this K. It's a vector, and that will be 2 pi over L times an integer here, an integer there, nx and ny. So that's really your momentum. It's a 2D vector. And h bar times 2 pi is just kind of the old Planck's constant, so it's h over L times all that. So you can check the units would be right in mass times velocity sort of units. And then from here you can also find your wavelength, energy, again h square over twice mass of electron times this squared. So this is a vector, so you can write it as that. And k dot k, I think that's clear. It's 2 pi over L whole squared times nx squared plus ny squared, right? The length of the vector squared, right? So that's again 2 pi over L whole squared nx squared plus ny squared. And that's your energy, but now it has 2 quantum numbers, nx and ny. This is a fancy name, quantum number. It just means this is the index of that point. That's all there is. I mean, there's nothing else, nothing more than that, right? But the fact is, this is quantized now, and therefore you can see now if I could even write it as h square, kx square plus ky squared over twice mass of electron, right? So I can write it like that. And now it's a paraboloid, right? It has a surface instead of just being a line like that. So we can sketch it. It's just all right. So kx and ky, and it would look, but it would have a surface. So it would kind of look something like that. Right? It's surface of revolution around the axis, around the energy axis. Now, one of the very important things I want to point out at this point now is that this is very interesting, and you see that each of these just a very casual observation will have a very interesting, profound effect later. We'll see that, right? Here, I can ask a question. Let's say I have an electron going in one dimension, this way, or I'm going to allow it to go that way too, right? So, and it has a certain momentum. How many other states are there? Let's say I would choose this. How many other states are there at the same energy, exactly the same energy, right? Meaning, in a free electron, if it's the same energy, you immediately know it's also the same momentum, but it's going the other way, right? So basically, the degeneracy is really 2. Other than this, there's only one other, right? Only one other. And they are related by what you call as perfect backscattering. So if it is going at 2,000 miles an hour this way, this thing is going 2,000 miles an hour. That's exactly the same velocity. Right? And that's in 1D. And later on, we'll see that you can actually kind of create something like that, in which case there'll be multiple. These will be, but don't worry about those. The moment I go to 2 dimension, that's not true, what we just said, right? You can see now that for any state, for example, I go here, and I say, well, here's a state. How many other states are there? First of all, if you ask how many other states are there with exactly the same energy, there are many. They're all sitting on this ring now, right? This is a circle. But then you can also ask with the same momentum, right? Same magnitude of momentum, then that's still true because they're all sitting on that circle, right? But if you want to say, for example, you can see that there will be something special about those states because they're related by exact opposite kx and ky mixes. And we'll see all of them will have a very important bearing because once we put these electrons, right now, remember, we are looking at free electrons in 2 dimensions. But we're going to put them in a crystal, and that's when we get differences between metals and insulators and semiconductors. The moment we put them in a semiconductor crystal, for example, these states, the degeneracy will have a very profound effect on the band structure and band gap and all that stuff. We're going to see that. But at this stage, just realize that 1D is very special. There's only one situation, and the degeneracy increases as you go to 2D, and obviously in 3 dimensions, even more degeneracies, right? Okay, so density of states in 2 dimensions. I think you can see now the way we will go about is you can, if you remember how we did it in 1 dimension, we kind of counted the number of states in K space here and said how many it is changing here in energy. Now in 2 dimensions, rather in 1 dimension, we could also visually see why as I go down in energy, my density of states will go up because they get bunching together closer, right? In 2 dimensions, it's a little counterintuitive, but actually as you go down, you can see that, well, I don't want to, you can maybe justify yourself, but what we're going to see now is you have a constant density of states. It doesn't change with energy in 2 dimensions as long as your energy dispersion is like this. It doesn't change. And that value we'll see in 2 dimensions is the mass of the electron over pi times h bar squared times, basically you can write it as a unit step function or a Heaviside unit step function that's 0 when energy is negative and 1 plus 1 when the energy is positive. So that's it's 0. So that's the, I can shade it perhaps if you want to look at, that's how the density of states is going to look as a function of energy. And then that you can get in a few steps again by applying the same trick. For example, here, what we remember, we will count in K space and then find how many in energy, right? We can go out in K to a certain, let's say a circle here, and let me sketch it here. Let's say I go out in K and draw a circle, right? And say that I'm going to now go between K, here's K, and a little bigger, which is K plus dk. I'm going to take a very thin ring, right, around it, and find that in that ring, how many states are there in the K space. I can count that easily, right? How would I count how many states, quantum states are allowed in that little ring, right? What's the method I should use? So first of all, what's the area of that ring in K space, right? The area of that ring is, right, 2 pi r dr, meaning it's the circumference times the thickness, right? Because it's a differential. You can, it's not exact because there are some square terms you miss. You can take this square, the area of that minus this, but then you'll get like a differential dk squared, which is very small. Anyway, the area of that is circumference times the thickness, right? Because the thickness is small, and that you can just write down as 2 pi k times dk. Dk is the thickness, and that's the circumference. And here again, I'm going to add in the fact that there can be okay, so that's the area. And how do I find how many quantum states there are? I know already the area of each quantum state. And that's just that, 2 pi by L whole squared, right? That's the area of each tiny square. So what we are really asking is how many of those tiny squares are fitting inside that little ring, right? So we just divide it by that. Right? 2 pi over L whole squared. So that's how many states there are. But we also know that in each state I can fit in 2 spins. Right? So 2 spins, so that's a spin degeneracy. So I can add that in here. In graphene and some other materials, you may have a valley degeneracy, in which case there's a copy of this in some other point in K space. You just multiply with valley degeneracy if you have it. Right now I'm not including that. So that's really it. That's how many states are there in K space in that window. And now we want to find how much, remember the energy is kind of a paraboloid coming out. So how many states are there in energy space? Because I'm really interested in the density of states as a function of energy. That's what I'm after, right? And that you can kind of write down. Remember, we're using this big G or uppercase G as the total number of states. But then I want the density of states per unit area. So I take this L squared here, right? So the big G is the number of states, and I want the areal density. Can scale it to the area, and that is what we're going to call as small g 2 dimensions in E, right? Right? Yeah. And now it's really easy to write down what is the density of states, because you see energy is like that, and I can take d by dk because I need that, right? So I can take that here and write it as dE by dk. You can see I'm doing something not quite, which may not look quite right, because E is a 2 function variable. It is function of kx and ky. But I think you understand, you can define it as a gradient, which is also okay. But if I just choose to work in the radial coordinate system, this is just fine. D over dk happens to be from here, just 2k dk, because this is k squared, momentum squared, times h squared by twice mass. Right? Right. And you see nicely here, you don't have to do any other substitutions, because well, okay, so I can sorry, yeah, d by dk is just that, right? And so I can take this, plop that in here, and I'm done, because the k actually cancels out, h squared by 2me, and I get my density of states. So this the k's cancel out. Let's say the 2. Did I miss a 2 here? What did I do? Yeah, that's fine. 2, 2, and 2, 2, and 2. Anyway, so you end up getting mass of electron over pi h bar squared. And clearly the density starts from 0 in energy. It starts from 0, so we put in the unit step. Right? Okay, so, and is that clear? So this is a kind of a very important quantity, especially in semiconductor electronics. If we look at silicon transistor today, the current that flows in a silicon transistor actually flows in a 2-dimensional electron gas. In every one of those billion transistors in our pocket today, in the cell phone processor, all of them, the on-off and zeros and ones are done. But when electrons flow in a 2-dimensional electron gas, and the density of states is indeed this, and this is what goes into the design of those devices as well. And we'll see later on that it has some very interesting impact on transport, quantum transport, like quantum Hall effect and other things that were discovered in the silicon transistor because of the 2-dimensional nature. So it's a very important. And so if you want to take away something, which you should always remember, is that the density of states is constant. It's proportional to the mass of the electrons. The higher is the mass of the electron is fixed, but later on we'll see this will become an effective mass of a semiconductor, but it's proportional to the mass. Yeah.
Professor, where does the quantitative terms come into play?
Okay. So what I want to say is it is this if energy is greater than 0, and it is 0 if energy is less than 0. That's what I mean to say. And this is a unit step function. I just kind of absorb all of these into a function that assumes a value of 1 when E is greater than 0. And that's also, so that's what I mean to say here. I mean, you could have written the same thing here too. You know, I just didn't kind of bother to. Okay, so that's the density of states. And I'm going to ask you to do a couple of things in the assignment. I'm not going to do that now, but let me just ask you right now that what will be the energy of an electron, the average energy of an electron if I fill it up to a certain Fermi level EF here, right? Instead of 1 electron, I put in, set 10 to the power 12 per centimeter square electrons. What will be the average UV here? Right. So anybody wants to take a guess or answer that? Meaning, what I'm saying is, in a 1D, it was clear if I fill it up here, I got like 1/3. It'll be exactly half. I mean, we don't even need to kind of think too hard because it's constant, so the average is half. And indeed, you can show, with all the integrals over Fermi Dirac, it's exactly half, and that's fine. Yeah. And because we are on that topic, when we go to 3D, we will see that the density of states is actually goes as square root of energy. It increases instead of dropping. It increases. It will increase as square root of energy, and there you can see that it will be, weighted above half, right? So, and then we'll see for 3. So in 2D, for example, this is getting. So in 2D, it will be half NEF, but just remember, in 1D, N is 1. It's 1 per unit length. It's number of electrons per unit length. In 2D, it's per unit area. In 3D, it's per unit volume. So we get a half for 2D, and in 3D, this is something you can do in the assignment. You'll get 3/5, which is greater than half. And so it's just from geometry you can explain that. So that's the density states of a 2D, and just for completeness sake, I'll write the 3D on the side and not try to derive all of them, but you can. I'll ask you to do a few. But in 3D, you can see that instead of a 2D space, you now have a 3-dimension. The third axis is also kx, so you have a sphere instead of a circle. You go a sphere, and then you go a little bigger sphere, take a shell, and find the density of states from there. Right? And when you do that in 3 dimensions, you will get, and I will ask you again in your assignment to go through this part. In 3 dimensions, you will get 1 over 2 pi squared, twice the mass of electrons over Planck's constant squared. 3 halves times square root of energy. Again, there's a unit step involved, but I don't want to write it. So it will increase as the square. So that's the expression for, this squared energy density states. Now we can ask a very important question now: the velocity of the electrons. Now the velocity is clearly 2-dimensional. It's related to the momentum, and in 2 dimensions, I can write now velocity is, to answer the question, what is the, actually, let me kind of step back a little bit and try to say that I have only discussed in class what is the current. I haven't really discussed in detail what is the velocity. In classical mechanics, velocity is, if you know the momentum by mass is the velocity. There's no other question here, right? In quantum, we have to be a little careful. We have to be a little careful with it because it's a wave, and for a wave, there are 2 kinds of velocities associated. There's something called the phase velocity and the other thing called the group velocity. So we have to distinguish those things. It's very important. At this stage, I don't want to get too far into that, but I just want to say that the velocity for a wave, if I look at the 1D version, which we ended up, here's what we ended up with for 1 dimension. And it looked, it's momentum over mass, no problem. Momentum over mass. This is also classically, if this was my momentum, which was mass times velocity, no problem. I get the velocity here, right? But we'll see not in today's class, but so you can see that I can write velocity as okay. So if I had momentum over mass, I could write it like that. But if I have, instead of a single state, if I had what you call as a superposition, if I had some states that are mixed up here, many k states are mixed up, and this is exactly what we'll need later. These are all, it's called a wave packet. It is composed of many different wavelengths, many different momenta. In that case, this is not the right definition. The definition, and this is a purely quantum mechanical definition. Let me write that down. We'll not derive it today, but we'll derive it later. So let's see, just from classically, p squared by twice mass is energy. And if I take energy derivative with momentum, I get p over m, right? No problem with that. And that's what we call as the velocity. This is kind of, if you do classical mechanics, or Lagrangian, Hamiltonian, whichever way, this is the velocity in classical mechanics. Now in quantum mechanics, actually, we'll have the same sort of definition, except I'm not going to think of it as a momentum over mass, but I'm going to define now a velocity like that. And in quantum mechanics, it's h bar times k, right? H bar by k. And just to take care of the fact that I may not be restricted to one dimension, but in different dimensions, this is a much more general form. I'm writing the same expression, but 1 over h bar, gradient of E of k. So this is essentially very similar. So this is a gradient, not in real space, but in k space. So d over dk, not d over dx or d over dy. Right? So gradient in k space, not in real space. Yeah?
Does this give us the phase or group velocity?
This is a group velocity. In fact, if you have a free electron in a solid, then the group and the phase velocity is exactly the same. If you consider a single state. If now I can mix them up, or if I directly put them in a crystal, already the group and phase velocities change. So as long as a free electron, they are the same, but this is the group velocity. It's the definition of group velocity. Yeah.
Isn't that almost the exact same equation as the effective mass?
No, the mass would be the curvature. We'll talk about that. We haven't gone to the mass yet. We'll come to the mass later. That's the curvature, the double derivative. Mass is the curvature of the energy. So physically, let's just see what is it saying. So here is just the first derivative, is the gradient. And you can imagine if I have in real space such a ball and I roll a ball down, it will go in the direction of the highest gradient in real space, right? That's how the ball will roll down, a hill or a valley, whichever way, right? And in the same way, here we have to visualize it in terms of the k space instead of the real space. And k space is really already taking into account that the electron has a wave-like behavior, and this is the group velocity. Now, at least qualitatively, you can see it's consistent with this first picture we had derived, right? And it is going to be completely consistent with our definition of current. If you remember, we had derived it from the wave function. We had psi star, grad psi, and all that stuff, right? It's also consistent with that picture. This is the group velocity of electrons. And maybe a little fine print I want to add is it turns out that this is going to be going to carry us through this course completely. We won't need any other changes to it. But over the last 15 years, since the discovery of quantum Hall effect, people have realized that there was one other term that people had neglected for a very, very long time. That's related to electric field cross what's called a Berry curvature. It's curvature of it's related to the geometry of the crystal and all that, which you can tune. But anyway, so I don't want. So this term kind of leads to a lateral velocity. If an electric field is this way, the electrons move that way, which happens in a high magnetic field or things like that, and then this leads to quantum Hall effect, magneto or resistance, what's called the anomalous Hall effect of magnets and things like that. I just want to kind of mention that, but for this course, I'm not going to consider that. I'm just going to restrict here, and this is a group velocity. So if I say, if that's the group velocity, you can physically see that For example, again, if I have an electron at this state in k space, the velocity is a vector that points, radially outwards, right? You can see from it's a gradient, and gradient of EK diagram is it's the slope, if you might. So it's the slope. If I consider a point here, it's the two-dimensional slope, right? So it's kind of, and if you want to project it, it will point radially outwards. So that state, if that state in k space is occupied, that electron is going, radially in that direction, radially outwards. And you can similarly say, obviously, the velocity of the state at the bottom is 0. It's not going anywhere, and that sort of thing. So and as you go out, as you go to higher and higher k, it is going radially outwards, and its velocity is increasing as you go out, right? Because the k is increasing, and if your energy is parabolic, then gradient is just proportional to k, and this becomes h bar k over mass of electron, right? If you have a free electron. And this is a somewhat simple concept, but it's extremely powerful concept, because later on we'll see that even when I put this electron in a complicated crystal with periodic potential, etc., this definition will still hold. And it's robust. It survives all the periodic potential and all that. But there will be one change, and that change will be that this mass is not the mass of the free electron, but something else. It's called the renormalized mass, the effective mass. But the group velocity will still remain the same definition. So the definition will actually withstand the, huge perturbation due to periodic potential. It will withstand it. So, yeah. So now, if that's the case, I can now write. So 3D, I'm not doing it in more detail, but from the velocity, I can write now that the current, and I'm going to write the current density now in in any dimensions, 2, 3, whichever way you want to go. The most general form of current. I think you can see that if you want to think of it in a quantum discrete way, what we need to do to find the total current is find the current due to each state and sum it. It's just that. I mean, there's nothing else to do. If you want to find the current, you just find the current due to each state, and this is a charge current, let's say we're going to talk about. So the electron charge sits here, and then I want to find, effectively I want to find n and v, right? But v is varying, velocity is varying for different k states. Different electrons are going in different directions. And n is the ensemble density per unit area or unit volume, right? So how do I deal with that? So instead of doing that, I find it because of one state. For one state, what is the, how do I write it? Maybe you can help me here. So how will I write the current due to a state k, single state k?
Q.
Yeah, q times. Right, so velocity of that state, v of, let's write it v of k in this way. And velocity is a vector, right? Yeah, I've written it that way. Let's write it as a function of k. Okay? Right, so that's that. And then I also, I have to do one more thing, right? And what is that? So remember, I need to have, it's not enough to just have that state allowed, but that state must be occupied. Right? If there's no electron in that state, then it could carry current, but there are no particles to carry it, right? So it must be occupied. And then that's something I have to add in here. And that's my occupation function f of k. And right, so that's the current due to any k state. And this is a perfectly general result. I mean, if you do metals, semiconductors, superconductors, this is a perfectly general result, right? As long as you have accepted the fact that electrons, being waves, are forced to have discrete k values. You have to now take this due to each k and find the total current will be a sum over all k's that you can find. Right. So you just sum it over all k's. Right. But just to be clear here, let's look at the dimensionality of the problem. And because what happens is there's one more term one has to put in here, and that is, well, okay, let me see. So in 3 dimensions, we know current density is in amps per area, right? Amps per centimeter square, right? Let's look at this. This is coulombs. And f of k is occupation function, no dimensions, right? Velocity is centimeters per second, right? And coulomb per second is amps, right? Coulomb per second is amps. So you see I must have a volume in the denominator, right? And this really should also have become apparent because there's an n here. It's per unit volume. It's not the total number, but per unit volume, right? So we must have over volume here. And volume is general. In 3 dimensions, it's per, 3-dimensional volume. In 2 dimensions, area. And 1 dimension is length. And initially, at this stage, I'm really trying to be very specific when I speak about volume because the dimensionality of electrons is an extremely important parameter in this course. 2D, 3D, 1D. And later on, I will not try to stress on it. But initially, I want to stress on this. When I mean volume, I mean area or length, depending upon the dimension, right? Yeah, OK. So really, this is another way of writing down the current. But now, you can see that this is kind of the many particle analog of the single particle current, single state current, which was given. If you know the wave function, you just write it down directly from that expression I'd written earlier. Now, if you have a lot of electrons, it must follow some occupation distribution function, Fermi-Dirac distribution, and so this is the total current due to many, many particles. And as an example, we can do the 3-dimensional current here and find out what will that give us. And what I was trying to say earlier is we want to show that we can recover Drude result from this quantum picture now, from group velocity and all that, right? So in 3 dimensions, we'll write it as Q. So I'm going to find the current density, right, which is in amps per centimeter square. And that's the electron charge over volume. Let's say I have a cube of volume L cubed. I mean, so instead of square, I have a cube. The electron is allowed to move, a lot of electrons allowed to move in a cube. And I'm going to sum over all k states that are sitting inside. OK, so just to be, I want to draw here. So physically now I have a cube, right? Each side is L. And so if I go to the k space now, I have kx, ky, and kz, right? And again, I have this discrete grid, each little cube, which holds one state. What's the area of that cube? Each small little. Yeah, 2 pi over L. Right, so that's just comes from there. And then if I have put in a lot of electrons, probably I filled up, instead of a circle, now a sphere. Right, I filled up from the center. I filled up all these little states at the edges of these or the vertices of these, fill them up till a certain level. And what we're trying to find is what's the total current carried by this. Now, if I don't have an electric field, I think it doesn't need too much imagination to see that the total current is going to be exactly 0, right? Why? Because yes, I have, but what is not obvious and typically not stressed in many courses is internally there are huge amounts of current flowing inside a metal. I mean, inside a metal, these electrons are moving at speeds of 10 to the power 8 centimeters per second because of Pauli exclusion principle and because of because all of them couldn't just sit at the 0 energy level, right? So they're moving at tremendous speeds, but for each state here, I have exactly equal and opposite state there, and they're completely cancelled out, right? So even at 0 Kelvin, they're moving at very, very high speeds, right? But they're completely balanced out, right? So that's why I have no net current, and so I can write that down now. That f of k is let's say f of k. Here, and velocity is h bar times k over mass of electrons. I'm assuming a parabolic dispersion, and applying this relationship, right? This h bar k over mass. And when I sum, if my f of k, let's just think about this part a little bit. If my f of k, which is the occupation function, how are states occupied in k space, right? Let me just sketch it along kx direction. And f of k in the kx direction. So I'm going to be filled with states from, say, minus kF to plus kF, which is the Fermi wave vector. I'm going to be filled at 0 Kelvin all the way till here. So F is 1, right? Its maximum you can fill is 1. And so I'll be filled all the way from minus kF to plus kF. Right? So all these states are filled. And f of k is a symmetric function around 0. It's symmetric, right? And as a result, you see you have a symmetric function around k. Kx is equal to 0. And what about velocity? Is it a symmetric or anti-symmetric function? I don't know. Is that the right word? Sorry, this is an even function. And this one is an odd function because it is positive on one side but it's negative on the other, right? And I think you know, let's say even and odd for even and odd. And so when I sum an even function and an odd function product over large area, you get a 0, right? Because you have equal and opposite positive and negative sign. So in order for any current to flow, you can see the thought process now. Unfortunately, this is not going to change if I apply an electric field. The velocity is independent of what you're going to apply electric field. The only thing you can change is the occupation function. Right? That's what's going to change. Velocity stays put. The band structure, all the energy allowed, quantum states of electron, they don't change at all with electric field or external perturbation. What changes is the occupation function. And pictorially, what will happen if I apply, let's say I apply an electric field. This is the x direction. Let's say my voltage I've applied is, I take this piece of material and I apply voltage. Let's say I apply a voltage in this direction. So positive voltage on this side and negative on that side, in which case the electrons, otherwise the current would like to flow that way, or the electrons will go this way, right, inside. So the field is pointing in this direction if I apply a voltage in that direction. And if the field is pointing in that direction, what that will do to these electron occupation functions is it's actually going to shift it. It's going to take a slice of electrons from this side, and it's going to pile them up on this side now. It will fill these and empty these out. Right? And now, when you sum it, it won't be 0. That's the, and then we'll get the Drude law and conductivity from here. So that's, if I were to sketch EK diagram, Kx versus energy, right? So energy versus Kx was a parabola. Sorry, yeah. And when I did not apply an electric field, it was electrons were filled up all the way till here. But then there was exactly equal and opposite and no current. Just one sec. And then when I apply electric field, now we're going to show that what I do is the population changes and I fill up a little bit more right-going states and empty out a little bit of the left-going states here. And these states are going to the left. And so this window is over which the current is flowing now. The net current is here because there's still current flowing here, but that's 0 because this is still symmetric. This is still even, so you don't. Yeah, question.
So when we were writing our function for the current, we said we had to include the Fermi-Dirac distribution function to determine if there is actually a particle occupying the state, but we didn't include the density of states, which would tell us if there actually is a state to occupy with that.
Very good point, very good point. So I'll come to that right now, but if I write it in K space and I sum it, the density of states is automatically accounted for here. If I write in energy space, I must multiply with the density of states. Because K space, remember how the density of states came about is we basically just summed over all the states in K space. So this already accounts for the density of states. It's already sitting there. In fact, the density of states in K space is always the same. It is 1 over 2 pi over L to the power, d, if dimension is d. This is the density of states in K space, right? I mean, because we already counted that. And so what we'll see now is when we go from here to the integral, the density of states will naturally appear now. It's sitting there already inside there when we sum it. Okay, yeah. There's another question.
You mentioned that the velocity doesn't change the electric field applied, but doesn't that affect the drift velocity?
Right. So the concept of a drift velocity, so in classical electromagnetism, the drift velocity the way to think about transport is I have a charged particle, right? And I apply electric field, and because of the force on the charged particle is Q times the electric field, right? and it's going to move in a certain direction and then scatter, and that's the Drude model, and it'll reach a drift velocity, right? In quantum, what we want to kind of completely stop thinking about that direction. Right? What we want to think of is the following, that the particle is already a wave, right? I mean, here, the electron is a wave, and it has a certain k states occupied. Right? It is sitting at a certain k state. Maybe we go here, so in 1D. So it's sitting, let's say, here. And then I apply electric field, and what's going to change is I'm not going to think of its velocity, but its k, the wave vector. That's what's going to change. So that's the wave particle sort of duality. You have to consider that the k will change, not the velocity. The velocity will be a consequence, but not the first fact. Right? And so the relationship I must apply to account for that is the force that acts on the electron or particle is h bar times dk over dt. This is what I should use, right? Not in terms of the drift velocity. And then what I do then, this is the procedure to apply. Use this, find your k at any time t later. Right? Solve this sort of rate equation, find the k, then go to your k space here and find the slope, and that's your velocity. That's the procedure we want to do. We don't directly say this is the velocity. We want to find first what is the k, then come and find the velocity. That's typically what we'll do here. Does that answer? I mean, and we'll see now, we're going to apply that, right? To show that we'll recover the Drude result from this sort of a picture. Right? Okay, so let's see. I wrote that force, but I'm going to write it as Q times electric field, and I'm assuming you understand Q is minus E, which is minus 1.6 times 10 to minus 19, just Q times electric field. This is the force. What I want to do is write down what is f of k, because we need a quantitative expression for the occupation function to find out what's the current. We cannot go further unless we know that, right? And I want to find that by a slightly different, but we go here and say that how are the k states moving? You know, as we saw, I mean, what I claimed was the electric field will grab electrons from here and put them there, right? But I want to find how are they moving, right? How, you know, k moved with time due to the response to this force. And remember, this is what you call as ballistic motion. There's no scattering anywhere. For Drude conductivity, you must include scattering or damping term. Later on, we'll see this expression is going to lead to quantized conductance and quantum Hall effect, all these other things, because there's no scattering in those things. But the moment you put in scattering, you must dephase it, and the way you dephase it is just put, again, the momentum over a certain scattering rate tau, right? This is the quantum version of the classical, you know, Newton's law, but with some damping. Same thing, right? And when you solve this, what you get is k. Again, when I say solve this, you can go and find what's the thing at steady state. Right? Under steady state, no change with time again, right? It will scatter, and the k's, physically what's going on is the electric field is driving the particle, you know, its k is increasing with time, right? The k is increasing with time, but then what we are ensuring that every time it reaches some sort of tau, it kind of scatters back here. So k increases, scatters back. So the k kind of reaches a steady state value. And that value here is steady state value. Again, I'm going to write roughly because it's really in that it's not, you can solve it exactly as well, but you know, in the steady state, you get Q electric field tau over h bar, and there's a minus sign, but that's okay. So that's what you get, Q tau over h bar times electric field from here. I mean, this term just goes away. And what you see is, I should write it as maybe, let's say, k naught or something like that. You know, that's the maximum shift in k you can get if you are scattering every tau seconds, right? That's the maximum you can go, because and you can imagine if your scattering tau is very, very large, then this can grow very large, you know. And what this physically this k0 is that if I had, you know, a distribution that was symmetric, how much k did it shift by? That's really physically what it means. You know, I mean, if I did not have scattering, this thing will keep moving and roll away, right? But the moment I put in scattering, it increases, then goes back, so it kind of gets stuck at that k naught. So physically, this k naught means how much did this distribution, which was symmetric, move with respect to 0. Right? So the centroid, or the mean position, moved by k naught. That's physically what it really means. And that k naught is directly proportional to the electric field and directly proportional to the scattering rate tau. Right? So yeah.
In like carbon nanotubes, you can get ballistic transport though.
You can, yeah.
So it just flows away.
Right. So so exactly right. What happens in the case, we are going to discuss that in detail, and we'll solve problems too as well. So if you had a ballistic conductor, then inside this window, it goes ballistically and there's no scattering, but it ends up scattering inside the contacts where the metal, once it reaches there, that's where it starts dephasing. But inside here, it goes coherently. You can do some beautiful experiments. You can actually have wave interfere, make them interfere and all that, because they're waves. You can do that. But yeah, so this is, there you can actually have, I mean, not just nanotubes. You can take gallium arsenide, 2D electron gases, and MOSFETs, silicon MOSFETs today. You have pretty near ballistic transport in these things. So because the distances are like 7 nanometers from one end to another in commercial devices. So it goes pretty much ballistically across. So yeah, but anyway, so that's the picture of where the k, or where the distribution function gets displaced to. And I'm going to kind of erase this and write down that expression for current now. And the claim is that it will become the Drude relationship, and I want to just kind of make sure that we get that. So the current density, what did we write here, is again electron charge over the volume L cubed, sum over the group velocity, which we have assumed is the energy dispersion is a parabola, and we have assumed that gives us this the group velocity times f of k, right? Okay. Now, what we can do is write down this f of k. So if the f of k was a Fermi-Dirac distribution, or ordinary Fermi-Dirac distribution, and it was symmetric, right? Then we know it will be 0, so I don't want to write that down. I mean, it's a symmetric function and a symmetric function. But here, this is a shifted Fermi-Dirac distribution. So essentially what we are thinking now is it is the same functional form. Now this is not guaranteed. We'll see later on in the course that you can actually do that. But this was the function, and the whole functional shape has remained the same. It just has shifted. So the center, your center of your axis has shifted. That's all there is to it here, right? Does that make sense? I mean, it's the same function, but just translated in k-space along the direction of the electric field. Why? Because this is the displacement. It's going along the direction of the electric field, right? And how much has shifted? Here's how much it has shifted. Right? Does that make sense? So if I had just put down the Fermi-Dirac distribution here like that, the sum would be 0. But what I must put then to find the total current is this. You can kind of write, okay, let's write it k minus this thing. Right? That's the shift of the function. So I get q tau over h bar times electric field. Okay. Does that make sense? I mean, that's how much k naught, that's the shift of the function. And now you want to sum this, and I think you can see I'm not going to try to sum that. I'm going to actually do a little variable transform. So I'm going to sum it over all possible k states. You can go to infinity. It doesn't matter. The Fermi function will die at infinity. It just, is whatever it is at finite values. But I'm going to just switch the variables and make it a sum over k prime, where k prime is this quantity now. I want to shift, I want to take this, I want to make this a symmetric function and this the asymmetric one. I'm just going to move those out. Just, a mathematical variable change. So I put k prime is equal to k minus q tau over h bar times electric field. And so what that will do is it will put in your Fermi function back here. Let's put it as k prime with a different index. But now on the right side, it will do k plus q tau over h bar times electric field. Do you see what I did? I mean, just a variable change. And then k prime, sum over k prime. And we go back and see again that, look at this thing here. K prime. That is still 0, right? So what we have done is, again, a symmetric function and a another asymmetric function or odd function. So that term is still 0, but this term is left out now, right? So it gives you the net current here, and you get Q over L cubed, a sum over K prime, let's say, okay, f of K prime times, I can pull out the constants, you get Q squared, tau, and you get a Planck's constant h bar out. I just pull those things out front. And then you get electric field. So electric field, you can pull it all out down to here, and we are very close to the Drude expression, right? And here I want to show that this, clearly this will be the conductivity, and you can already see all the signs. There's a Q squared, there's a tau, there's a h bar. And you know we are going back from quantum to classical now, so the h bar will cancel. It must cancel because in classical mechanics there's no h bar, right? And we see that now. And this will also try to answer your question that where is the density of states. So now I'm summing over k states, and it will appear now here, right? So whenever I sum over k states, I can convert it, as we have talked about, into an integral, right? And the way to convert a sum to an integral here, again, important point, is we integrate over k space in 3 dimensions. I'm going to write it as dk with a, this is a confusing thing, but this d is the dimension, right? So in 3 dimensions, dqk, 3 dimensions d square k, and 1d is dk, right? Yeah?
You have 2 terms, and now you only have 1. How did that happen? I mean, I can understand factoring out the constants, but f of k should still be multiplied to E as well.
F of k should be multiplied by E electric field?
Yeah.
Yeah, so what I claimed was, there are 2 terms for the velocity. Now, because I shifted the origin coordinates, so the k plus this.
Yes.
Now the k and this term is still back to even and odd. The sum will be 0, so I threw it away.
Oh, okay.
And this is the asymmetric part, so I just retained that one.
Okay.
So yeah, this term is essentially, even after I shift the distribution here, there is a part of this distribution that is still symmetric, right? So I just throw that out. You can evaluate it, but you'll get 0, right? So yeah.
I think in your last expression, you shouldn't have an h bar in the denominator, and you should have an me.
I shouldn't have. Say that again?
There should be no h bar. The h bars cancel, and you should have an me in the denominator.
Oh, you're right. What did I do here? Yeah, I haven't taken out these 2 terms. I must, right? And that already does that. H bar, cancel that h bar. Right, thanks. Yeah, right. So yeah, you can see this h bar will come out, and then we'll cancel out that h bar from group velocity. It's gone, right? And then now it's back to classical. And I'm just trying to show now that when I sum this, or rather this big integral out here, and with this L cube, we'll get, that's the electron density. And physically you can see what we're doing now is just, we're counting how many electrons there are, right?
Should it be an integral over dk prime?
Yeah, you can, yeah, that's right, dk prime. And you're right, this is a dk prime, and it's an integral, and I'm just going to take the L cubed here, but physically you can see that if I sum over all states in k space, I just get a total number of electrons. And then you have L cubed in the denominator, so that's n, electron density. But I want to also do one more thing here. When you want to actually do evaluation of such integrals, I want to point out how do you generally do that. Whenever I'm going to integrate over k space, I'm going to take dk, and so you can see that there's a little bit of a problem just writing a sum as an integral with k, because there's a dimension here. dk has dimensions of 1 over length, right? Yeah, is that, I mean, it's not, you can't just say that I'll replace the sum by an integral like this. I must take into account the dimension. And in the discrete grid, this is where the, one must divide it by 2 pi over L whole cube. Does that make sense? I must divide it, because when I sum over states and convert into an integral, I generally have to multiply with that delta, right? And here the delta in d dimensions is a volume, in 1d it's length and all that, so I must divide it. So what I mean to say here is whenever I do sum over k space for any physical quantity which is changing in k, I'm just trying to sum it. When I do an integral over any dimension in k space, I must divide it by 2 pi over L to the power d. I must do that. And I just plop in whatever function I want here. It can be the velocity, the current, the spin, whatever be it. Just plop it in, but this is the conversion. And the density of states is sitting inside there. Okay, so I will not try to do this. We'll see this applied a few times later on, but I want to write it that this quantity is really the electron density times electric field and current. And this is your Drude conductivity, which is the same as before. But it's now, you see, we went through this process because you can see how physically you might want to calculate the current of an ensemble of quantum particles instead of a discrete one. Yeah?
I just want to double check this. So the integral of f of k over 2 pi L cubed is equal to capital N in this case. And the capital N over L cubed is little n.
Good point. Yeah, say that again.
So the integral of dk prime over 2 pi L cubed times f of k prime.
Okay. Yeah, I see what you mean. So
essentially, are we pulling out that 2 pi over L cubed, or does that equate to?
Sorry. Yeah. let me make sure I do it right. So f of k, q, and if there's a L cubed here, that's velocity, charge. So you get amps, and there's a length in the numerator, length cube in the denominator. So we are in the right dimensions here. Now, if I go from sum to an integral, yeah, okay. Let me just rewrite this a little bit so that it's clearer. Maybe I did a little bit of rearrangements here. Q over L cubed, right? And I'm going to now convert it into an integral, and this integral is over volume, right? D cubed k, 3 dimensions, let's say, over 2 pi over L whole cube, right? So this integral becomes that, and everything else stays the same inside, right? So f of k stays f of k. You can write it, I mean, it's k prime, it's a dummy variable at this point, it really, yeah. And then all these quantities have no k in them, so I can take the q, tau, and h bar out here, get q square, tau, and h and m, h bar cancel. There's a mass here, right? Does that make sense? I mean, that's all fine, yeah. And now, so the L cubes and L cubes go away, right? So the volume should cancel out because current density is a physical quantity, so the volumes cancel out here, right? And I'm left with this f of k and this quantity now, right? And now, what I was trying to really get to is this quantity physically. You can check what are the dimensions. I'm sorry, and the electric field here. Right. And this quantity is n, the electron density per unit volume. This whole quantity here. Does that make sense? I mean, you can see that the volume is already, it's a volume. K is 1 over length, so it's taken into account here.
Okay.
Yeah, that's equal to n. And the same relationship holds for 2D, for 1D, and all those situations. It will be the same deal, really. Yeah. Any other questions here? All right, let's see. So if not, I'll try to end the class today by saying that, so we have covered, this is the free electron model. And with it, you can explain quite a few things about metals, but you can't make progress into even explaining why are there insulators and why are there semiconductors. And that's a big problem. And for this course, at least, it's a big problem. So how do you go to the next step and say that I have certain elements or certain materials that may be, if I apply an electric field, nothing happens, there's no current. So what's going on? Why is that, right? And because this is telling you that if I have electrons, I should get this sort of Drude conductivity. But we know that there are, if you look at aluminum nitride or some wood or glass, or if you look at a crystal with a wide band gap, there's no current. And that picture will come immediately from here because here's what we're going to do in the next class. I'm going to just set up this problem today. Do that in the next class. So we have electron distribution for free electrons that looks something like that, right? And we know now that the electron is not going to be in a vacuum environment, but it's going to be in a crystal. Right? We're going to put a crystal in the path of the electron. And instead of a free electron, there will be a crystal is a periodic arrangement of atoms. So it's going to introduce in the path of an electron a periodic potential. A periodic potential. And the moment I put in a periodic potential in the path of an electron, you know electron is a wave, right? And its wavelength is changing as you go from 0, k is equal to 0, the wavelength is very long. And as I go up, because k is 2 pi over the wavelength, right? As I start increasing, as I go to the right, the k increases and its wavelength is getting shorter and shorter, right? Right? And it'll get shorter and shorter, and at some point of time, meaning once it reaches a certain length, so this periodic potential is going to be determined by the distance between any two atoms, A. Right? That's the periodicity. Right? So the potential is also a wave, if you think of it. It's standing wave. It's just standing in the way of the electrons. And the electron is also a wave, is going through. And I think we all know that when the two wavelengths match, then a lot of things happen. Right? If the wavelengths don't match, not much things happen. The wave can go through as if there's nothing there. Right? But the moment the wavelengths match, you get quite a bit of scattering and interference of the electron wave with the potential. Right? And therefore, what it will do is it will actually create standing waves at those wavelengths at which the wavelengths exactly match. Right? And what will happen to this distribution then is, so as I increase the k at some point, which is going to be, let's say, pi over the lattice constant A, you can show that the wavelength of the electron and the periodic potential wavelength will become exactly equal now, right? Now it interferes very, very strongly. It interacts very strongly with the periodic potential. And as a result, what happens now is if there was a state of electron allowed here, which can propagate because of this sort of diffraction grating of periodic potential in the path of an electron, it will not be allowed to propagate anymore. It will form a standing wave. Right? And what that does to the energy of the electron is very interesting. It splits that energy into two. It splits it into two energies. And one of them will go down, and the other will go up, and there will be a gap introduced in this energy spectrum here. Right? And so what it will look like is, okay, so let me sketch it out. It will look like this. And once I'm done, we'll show this in detail in next and following classes, that you will form these bands of energies where the electron has diffracted and is not capable of moving in the material anymore. So that will be a gap. And then with these bands of allowed energies, there will be bands and gaps and bands and gaps now, right? So, and so we will precisely calculate how does it split, how does, and these curves and all that, right? And you can see now that if I have this situation where I have allowed energies gap, allowed energies gap, this is very similar to in a periodic table when you move across atoms, right? You have very reactive atoms, and then you have noble gas, right? It kind of, the shell closes, and suddenly you have completely unreactive element. Then you go to the left again, very reactive, and you increase. And so it kind of periodic closing of orbits happens for atoms. And exactly the same thing happens for a solid or crystal. If I have bands and gaps and bands and gaps, and I start filling electrons, right? I fill electrons, and I fill up, and then I fill up this whole, if I have filled half, it's a lot of empty shells are available, empty states are available, so it's a metal. It can conduct nicely because electron can go from here to here easily with electric field. But then I fill up one of these completely, then it's just like a noble gas. It shuts its shell and it's an insulator now. And then again, metal, insulator, metal, insulator. So as you go across the periodic table also, you go through metals and then insulators and semiconductors, and then come back, metals, insulators, semiconductors. So you go this periodically as well, right? Same deal. But all of that happens because the electron now experiences the periodic potential. And now what we have to do is look at one new thing we haven't done till now. We have talked about Schrodinger equation, but we must now look at how do electron energies, how do electron wave functions, momenta get changed if you put it in a periodic potential, right? So that's, the treatment for that is called perturbation theory, grand name, but all that it says is how did these things change? What was the new form of the wave function? What's the new form of the energies? So I'll post a handout which will have perturbation theory, and it's also on the slides that are posted, by the way, so please start reading that part. And this is kind of the new thing that you we actually will kind of need a little bit of that in this course, so please read up that part. And then once you're comfortable with perturbation, with the results, I don't want you to kind of completely understand, I don't need you to completely understand all the details of perturbation theory. If you haven't had it. If you had it, great. It will be a great experience of applying it and learning things. But if you haven't had it, there will be a few results. If you can at least qualitatively understand what they are, and we'll need to apply those. That's what we need to do. So those things are written up already on the slides here. So if you look at, this is the set of slides where it's written up, and you can start reading this. We are kind of done with first 4 or 3 handouts that are on the slides. We're kind of done with that, and we're moving into this now. And I will post a set of notes as well. Okay. So and please read these slides, because everything I derived in class has been done in much more detail in the slides. So please do that. Okay. So we'll meet next Thursday, and Tuesday is a holiday. So. Yeah.